Hello everyone. This is General Interest SHARCNet webinar. I'm Sergey Maschenko, the today's presenter. So the today's topic is debugging OpenMP programs. So let's go through outline. So the plan today is to go through a few slides, probably spend 20 minutes or so, and then spend most of our time going through live demonstration, debugging actual buggy OpenMP programs I created for this presentation specifically. And this webinar is a continuation of a series of debugging webinars we are running at SHARCNet. I delivered MPI debugging webinar last summer. And don't be surprised, those who attended, you'll see a few first slides are common with the previous seminar. And there are good reasons for that, because at the most general abstract level, parallel bugs are the same for any kind of parallel paradigm you're using, either MPI, OpenMP, CUDA, and so on. So we'll start with the introduction, and then I'll give you a very short overview of the debugging tool I'll be using today, a commercial debugger DDT, and then we'll have the OpenMP debugging demonstration, and then there'll be time at the end to ask questions. All right, so let's start with the introduction. Most of you probably familiar with serial code debugging if you did any code development. And normally people have some serial code experience, programming experience, before they start dealing with parallel programming. And so you know the main stages required to do code development, whether it's serial or parallel. There is a designing stage, coding stage, debugging stage, profiling, and maintenance. The reality is parallel programming is more difficult than serial each step of the way. At all of the stages, parallel code has more challenges than serial code. I'm not going to be covering most of these points. For the purpose of today's seminar, we'll be discussing the middle point, the debugging, and specifically debugging of OpenMP programs. In a buggy OpenMP code, most of bugs will be the same kind as you would encounter regular serial code, like segmentation fault, when you, for example, writing out of boundaries of array or using wrong number of arguments for a function, something like that. We will not be covering those situations here, even though the debuggers, DDT, for example, are perfectly fine to detect those bugs. Instead, we'll be focusing on parallel specific bugs, which fall mostly in the two following categories, at least in OpenMP context. One kind of bugs is about race conditions, and the other kind of bug is about deadlocks. So let's consider those two situations in sequence. So what is the race condition? In an OpenMP context, you get race condition bugs when you misuse shared variables. So for those who are not very familiar with OpenMP, in OpenMP you can label, in fact you have to label any variable you use inside parallel region as either shared or private. And that labeling can be done either implicitly by the compiler, or in fact it's much better way if you do it explicitly. So a typical way to misuse shared variables is when you use implicit labeling, and then that forces compiler to mislabel certain variables mistaken as shared, where in fact it has to be private. And second situation is you're a more experienced programmer. You know that variable has to be shared, so you label it as such, but you forgot to serialize access to that shared variable. So shared variables are dangerous only when you update them. So when threads start updating shared variables, that's when you create condition for a race condition. If all threads, all they do is just reading shared variable, you cannot create race condition bug. But if at least some of the threads write to that location, update the variable, then there is an opportunity for race condition bug. And having an issue of the first kind, the risk of that can be greatly reduced, especially if you're a beginner. So please don't rely on default labeling of shared versus private variables in OpenMP. I bring up example of old Fortran style versus C style. One of the disadvantages of Fortran programming was the fact that there was implicit type involved. And the first thing you do if you want to write good style in Fortran, first line you put implicit none to disable that behavior, because this is very bug-prone behavior. So this is similar situation. Please do not rely on default labeling of OpenMP, and each parallel pragma you create, you have to put default none clause. Once you do that, then the system will force you to label explicitly all the variables you use inside parallel region as either shared or private, or perhaps first private or last private. And if you forgot to do that, you'll get compilation error. You'll be forced to go back to think carefully which variable has to be shared and which variable has to be private. And the general rule, if you want to minimize chance of race conditions, you have to try to make most of variables private, only those which need to be shared, either because you use them to communicate between different threads, and shared variables is the only way to communicate between threads, or for other reasons, for example, to save on memory or make the code more efficient. Then in those situations, shared also can be required. But just treat all shared variables you create very carefully, as they prone to this race condition bug. So another risk factor listed at the bottom is no wait clause, which can be added to many OpenMP pragmas constructs. And what it does not change the computational part of OpenMP code. It just might improve efficiency. And but putting no wait clause can create conditions for race condition bug. So use it carefully. It should be no harm to remove no wait clauses everywhere. The results should still be correct. So if in doubt, if you think one of those no wait clauses generate race condition bug, one strategy is to remove all no wait clauses, see if it fixes the issue. If it does, then you put it back one by one to see which particular no wait clause does that. DDT debugger can help you at least to zoom in to see which parallel region is at fault. All right, let's move on. So how does it manifest itself? The typical manifestation of race condition bug is when you get wrong result and you get different results, either sometimes or all the time. The latter part is especially indicative. If just it's a wrong result every time, maybe, but maybe not. But it's very clear indication of race condition. Every time you run, you get different result. That's a very clear sign you're dealing with a race condition code. And as I mentioned before, shared variables are the ones you really have to be paying attention to, because they are the sole source of race condition bugs, specifically the part where the thread is updating value of shared variable. That's when you can create race condition bugs. A very simple example of race condition. We have sections, parallel section. So there are 3 threads executing 3 lines of code in parallel. So all 3 variables are shared, A, B, C. And obviously the final result will depend on the order of execution. Remember, in OpenMP, order of execution of threads is not guaranteed, and it's pretty much unknown until execution time. So every time you run your code, you're going to get different result. How to fix this bug depends on what you're trying to achieve here. If the goal is to use pre-existing values of A, B, C to update to future values of the same variable, then these should not be shared. Instead, they have to be labeled as private, in fact, first private. So if you say, instead of shared, you say first private ABC, then you produce the correct behavior, because each thread will get a private copy of A, B, C, and then it will update those variables. So then the bug is removed. Second kind of bug is deadlocks. And it happens when threads lock up waiting for a resource that will never become available. The sign of deadlock, program is frozen, it's stuck. It doesn't proceed, nothing happens. It hangs indefinitely. And there are quite a few different ways to create deadlocks in OpenMP, and I will consider just a couple of examples. And depending on the kind of deadlock, there are different prevention strategies. I just mentioned a few advices. For example, once you start dealing with explicit thread IDs inside parallel region, be very careful, especially if thread IDs become an argument in a conditional clause like if. So if you say, if thread ID equal 1, I do this. If it's not equal 1, I do something else. Be very, very careful, because this is the perfect situation to create a deadlock. In particular, because some common OpenMP constructs, like for, do, work sharing construct, single, some others, they require that all the threads in the team reaching them. Obviously, if you say if thread ID is equal 1, you might prevent certain threads reaching constructs, and that will instantly create deadlock, as I will show in a live demonstration. Another example I'll be showing later, when you don't use properly flash pragma. So in OpenMP, if you need threads to communicate between each other, they do that by updating a shared variable, which you can call a flag. So one thread updates the variable, and the other thread reads the value. So once the value changed, it's the signal that the other thread has to do something else. So the communication has accomplished. That works fine, except for the fact that there is cache. Each thread has its own cache version of that shared variable. And when a thread updates a value of shared variable, it's not instantly propagated to the actual shared variable. Same happens on the reading side. When thread reads shared variable, it might just read the local cached copy, not the actual shared variable. So it's important to always use flash pragma after update of shared variable by one thread, and before reading by other thread, you have to also do flash on that variable. That makes sure that all threads deal with a single copy or version of shared variable. And as I will show later, the strategy to fix certain bugs, which can manifest themselves as deadlock bugs. And another way to create a deadlock is to forget to unset lock after setting them. And I probably will not have time to show you the example, but you will get a chance to copy all the files and to play with them yourself later. And here's an example of a deadlock. It looks a little bit complicated. Basically, there are two sections, two threads executing in parallel, and we're using two locks enclosed. So we have first set lock A, then set lock B by one thread, and then upset in the opposite order, and the opposite order for the other section, B and then A. And then what happens depends on the execution timings. If first thread executes all these statements, then nothing wrong happens. The second thread can execute these statements and no problem occurs. But if more likely both of them will start executing their respective statements more or less simultaneously, then they'll both get stuck at the second line, because at that point both locks will be locked, and they'll be waiting for the other thread to unlock the other lock, and it's not going to happen because both threads are stuck in the deadlock. So here we have situation, a deadlock bug, which manifests itself sometimes. So sometimes program runs, sometimes it hangs. One advice here, probably it's a bad idea to enclose locks this fashion. If you have locks, use it as single layer. Don't create two layers of locks. It can be dangerous. Given those two common kinds of parallel bugs, which tools to use to deal with them, to detect them? So I'll be discussing specific programs we have in SHARCNet, and let's switch to the description of these two. So one of them is a general purpose debugger, DDT, installed on a few different systems. And this is a commercial debugger which is suitable for debugging serial job and all kind of parallel jobs, MPI, OpenMP, CUDA, and also any combination of those, which makes it a very powerful debugger. Also, it includes a memory debugger, by the way, which is off by default. The very first run you run the code, you have to click to enable that. We will not need that feature for today's presentation. This tool is suitable for all programmers levels, from beginner to an expert. If you're a more advanced programmer, then you might find very useful the other tool, Valgrind, which is an open source memory debugger. Apparently very good for debugging OpenMP, but it's fairly advanced, and we will not have time to go through those advanced features. So we will focus for the rest of the talk on a specific debugging tool, DDT. If you need to know more detail, please check the software page on our web portal dedicated to DDT. So let's go to overview of DDT. So as I mentioned, this is a powerful commercial debugger with graphical user interface, GUI. And that makes it one of the few exceptions when we do allow users to run interactive graphical application in SHARCNet. Of course, there are special conditions where and how we can do that. I'll show you later. And it's suitable for debugging serial and parallel programs. It was developed by Alinea from UK, and we've been using it for 10 years now. It's installed on 4 different clusters. The most up-to-date version is installed on Orca and Monk. This debugger supports C, C++, and all flavors of Fortran. You can find detailed documentation, the user guide installed on our cluster in this specific location. Asterisk stands for version. We have multiple versions installed on clusters, so you can look up specific version user guide. And we also have online tutorial. So go to our wiki help section and search for DDT debugger. Basically, you can find it there. Before do any kind of debugging, whether using DDT or some other debugger, you have to compile your code special way. You have to generate symbolic information, which is required by any debugger. And you do that by adding -G flag to all the compiling statement inside your makefile, or if it's just a single file, just add it to compiling command you're using, whether Fortran or C or C++, just add -G. Normally, you debug the code with optimizations disabled. That makes it more easy, more straightforward. So you say -O0. This way you disable all optimization. But as I will show one of the examples, sometimes you have a situation when a certain bug manifests itself only at certain optimization level. So you don't have a bug, or it doesn't manifest itself at 0 optimization, but you say 1, O1, you have bug. In that case, you have no choice. You have to debug your code with proper level optimization. As I said, this is interactive GUI applications. It's an exception. Normally, we don't allow users to use those applications. SHARCNet basically allowed to debug only using development nodes. The exception is a recurring cluster where you can use test queue, but I don't have time to go to explain that today. So normally you have to go to development nodes. So on Orca, you SSH to Orca, and then you SSH to one of the 4 development nodes, Orca Dev 1, 2, 3, or 4. Kraken has 8 development nodes. And another important point, because it's a GUI application, which is you normally don't deal with in SHARCNet, you need an extra support, an extra feature on your workstation. You need to support for X window. Basically, you need an X window client. So if your workstation is Linux, it's already there, nothing to do. If it's Windows, you have to install program mobxterm or a similar program. If it's Macintosh, then you can use free program X Quartz. So for more details, please check this wiki page, remote graphical connections. Just search on our wiki help, remote graphical connections. So finally, once you've done that, once you ensure that your workstation has X window client, and of course it has SSH client, and then you log into one of our clusters which has DDT like Orca, and don't forget to add argument switch -Y all the way. Each SSH statement you do, you have to add that. That enables usage of graphical user application over SSH. If you forget to do that, you won't be able to launch DDT. So what you do normally, you do SSH-Y user name at, let's say, orca.sharcnet.ca. Then you find yourself in a login node, and then you go on to SSH to one of the development nodes. Again, don't forget to add -Y. And once you're there, you have to load the DDT module. Say execute module, load DDT. After that, once your code is compiled with -g, as I showed in the previous slide, all you have to do is to say DDT, path to your code, and if your code takes arguments, then you can add them here. And then execute your code using a graphical user interface. And the way it looks, it's something like this. Once you launch the main window of DDT, there are many, many nice and useful features here. I absolutely have no possibility to go through all of them. I'll just mention a few points, a few highlights. So convenience of DDT is in part due to the one-click access to all processes. If it's MPI, if it's OpenMP, same with all threads. So you just click on one of those thread ID, and you get instant update inside your main window, which shows you the code, the current state of your particular thread. Then you have advanced source browsing, one-two-click access to any function inside any files compiled, used in that particular binary. And another highlight is literally highlight. It's syntax highlighting. It's quite convenient when you deal with large codes to have the ability to see different colors, different fonts. It just adds this extra niceness feature of DDT. All right, so we are done with the preliminary part, with the slides part. So now let's switch to live demonstration. And for those few of you who already have the X window client set up, you might want to consider follow my live demonstration by doing it in parallel yourself. So only for those of you who already have X window client. So what you do now, you use your SSH window, your SSH-y, capital Y user at orca SHARCNet.ca, replace user with your username. Then you use one of those development nodes. And then all you have to do to copy my examples, don't forget -R to copy the whole directory, which is located /home/syam/open, capital MP, and then asterisk, space, dot. So that will copy the whole directory. You'll get some error message. Don't worry, because two examples I cannot share with you, unfortunately. We use it for teaching purposes, but the rest of the examples will be copied correctly. And then you just change directory to the one you just created, and then you can follow my examples. So we have roughly half an hour for live demonstration, so I'll try to be efficient. As I said, I'll show just a few examples, not all of them. I don't have time to do them. What you see here is my shell window. I haven't logged in yet to SHARCNet. So first I do SSH-Y, my username, SYAM @orca.sharcnet.ca. So normally ask for password. I'm running SSH agent. This is SSH keys, and it's a convenient feature. I don't have to type password every time. And then I just do SSH-Y orc dev, let's say dev4, one of the 4 development nodes. It's a good idea to check using top command how busy the node is. It's a shared node, can be very busy. Right now you can see the top, it's essentially empty. No one is using it for anything intensive. And then we're going inside that OpenMP directory I was referring to. So as I said, if you copied my examples, you will see X files, but the primes count examples, you will not see them because they are not user readable or other user readable. But let me actually start from one of these examples. So let me demonstrate the specific bug, which is a race condition bug. So let me use text editor nano and to open this file. So this program is an OpenMP program which uses a brute force approach to find all prime numbers between number 1 and I think it's 6 million. It should run like in half a second on 24 threads. And it only counts, not like it doesn't list them, just counts them. And don't worry about these parts of the code. I just want to focus on the parallel region, which starts here. And this is actually correct, good version. Remember, I told you to always use default none, and that on each parallel fragment. That forces you to label all variables used inside parallel region as either shared, as is the case with sum variable. And by the way, sum it has to be shared because later on it's been used for work sharing construct as an argument to reduction clause. And that's the rule of OpenMP. Variable use argument to reduction clause has to be shared, otherwise it's not going to work. So that's why it's shared. And the rest has no business being shared, so that's why I labeled it private. And that's the correct approach to do. But let's say we are beginners or we are lazy programmers. We don't do any of that. We just say program OpenMP parallel and just hope implicit labeling will just work for us. So I'm going to save the program and I will try to execute it. So I'm going to use first our default compiler CC, which is actually Intel compiler, ICC. I'm going to say -G. Remember, that's what you need for debugging. I'm going to set 0 optimization, and I'm going to add OpenMP because this is an OpenMP program. And then I'm going to compile my code, which I know is buggy, but let's see if it's going to manifest itself. So this created a binary A out. So let's execute A out, and okay, here we go. So by default, the OpenMP program will try to use number of threads equal to number of CPU cores, which is 24. And by the way, that's going to run forever. So let me actually use optimization just to accelerate things. Okay, you got your result in only 0.4 seconds. By the way, it really emphasizes the value of using proper optimization. So the difference in this example is factor of 10 or more. So this speed up. So it's a huge difference. So this is number of primes. So let's say I don't know what's the correct number. I can tell you this is the correct number. But let's try again, and again, and again. It looks like there is no bug. So this is interesting. Actually, I discovered yesterday when preparing this seminar. This is one of the bugs which it does manifest itself under Intel compiler. So Intel compiler seems to be doing something smart, sort of bypassing the bug. So let's try GNU compiler, GCC. So the only difference here, you have to say instead of -OpenMP, it's a -F OpenMP. Oh, and then you have to add link to math library. That's the other difference. So now we're running the same code. It runs a bit slower. Okay. It seems to be doing the correct thing. Let's see. Okay, now here we go. So we got, oh, in fact, even the first one was the wrong result. So every time we run the code, result is different. And if you know the exact result, the correct result, which is actually here, you see it's never correct result. It's always wrong and it's always different. That's very clear manifestation of race condition bug. And I have to emphasize this is interesting situation. It does not manifest itself on the Intel compiler. Intel, it does something sort of smart. But in a sense, I'd prefer my compiler to be dumb about it. I prefer if there is a bug, which is definitely the case here, I want it to fail me right away. Because if you always use Intel compiler, you think you don't have a bug. Then you switch to other environment where you use GNU or some other compiler, and all of a sudden you have a bug. So in a sense, it's a nastier bug because it manifests itself only under certain conditions. For example, under certain compilers. Anyway, so let's stick to GCC from now on, and let's see what exactly we can do about it. So we got pretty clear manifestation that this is apparently a race condition bug because we get wrong result and different result every time we run the code. So let's use DDT. For DDT, I prefer to disable my optimization. It's going to run slower, but it's more predictable debugging. And then I have to load module, load DDT. So don't forget, we already have to be inside our development node to be able to use DDT. And then all we have to do, we have to say DDT and the path to my binary. There is no command line arguments, so just that's sufficient. If my X-Window client is running on my workstation, and if I didn't forget to use --Y all the way, each SSH command I used to arrive here, I should see a popping up window of DDT. That's what I'm seeing here. And those of you who are following me would see as well. So it correctly detected this is OpenMP. By the way, by default, first time you run DDT, the memory debugging is off. There is no mark here, and let's keep it there. We just don't have time to go through memory debugging, and it's not part of today's seminar. And then here you can choose how many threads you can use. I don't know, let's say 24. That's what I used previously. And let's run my example. So that's all you have to do. Just make sure you choose correct number of threads and just press run. And now you go to the main DDT window, which you've seen slide before. There are many, many different features, nice options you can avail here, but I don't have time to explain everything. I'm just going to tell you that the solid line, highlighted line, which is also contoured, has a black contour, is the view of the current thread. That's where the current thread is actually located at. And because, unlike MPI, which has all the MPI ranks created from the very beginning, here we can see only a single thread created at the beginning. Only once you go inside parallel region, you will see multiple threads. Once you exit parallel region, you go back to single thread. You enter second parallel region, again you have multiple threads. So this is different situation from MPI code debugging. You can do debugging two different ways. Either go step by step by step, line by line by line. So you press one line and you go to the next line. And you can see right away that the current line variables, their values are displayed here. You can go anywhere else in the code, click, and you see values of all the variables displayed here. You can also highlight a range of lines to see all the variables from that range shown. And that's a convenient feature. And or you can use second mode, you can use an MP3 player. You just press play, wait a little bit, and then you pause. And then whatever random state you end up at, then you can analyze your code. So we'll be using mostly that mode. It's actually much faster if you know that's what you need. If it's going to work for you, that's preferable. It's faster. So let's press play and then press pause. All right. So what you can see here that there are all 24 threads. You can see that we pause in some random state where there are actually a spread of values. So different threads are at different lines of the code. You can see that from multiple highlighted lines. You can see highlighted here. And usually how densely highlighted shows you how many threads stuck at that particular line. To get more particular information, hover the mouse, and it tells you which thread. So you can see there are 11 threads at this particular line of the code, including the current thread, which is thread number 1. And you know that because this is the only highlight which has black contour. And you can see here there are other lines stuck here. There are 13 lines here, and also there is a certain one line here. So that's interesting information. So what else you can do? You can switch between different threads, single click. So you can say this particular thread number 6 is at this particular line, and so you can do like that, go on. That's kind of neat, but does it help us? So race condition bugs, actually, they're not particularly easy to detect. Basically, a debugger doesn't really know race condition is going on, and that's why it's hard to catch those. So compiler cannot catch those. And so the way to deal with those, first you detect it, you get those different results every time you run your code, and then what you have to do, because only shared variables can create race condition bug. And only steps when you update shared variable are prone to race condition bug. So first order of the day is to discover all shared variables. And that's especially critical if you used implicit labeling, as is the case here. And the trick here, how DDT can help you, once you press the pause, so all threads stuck in some random state. So what should happen, if a variable is shared, the value of this variable should be the same across all the threads. And by the way, that's manifested here. So success is a shared variable, apparently. Here's the value, and here's the horizontal line. What does it mean? So let me show you actually first all the variables. So I'm going to drag my mouse across all the shared region lines. And now I see all the variables used inside my parallel region. And you can see actual values for that particular thread ID 12. But also interesting situation here. Some variables have solid horizontal lines, some have kind of noisy behavior. So this is pictograms showing the spread of values across all 24 threads. So those variables which have exactly the same value across all the threads have horizontal solid lines. And these variables are likely to be shared because shared variables will have to show this behavior. Some private variables also might show that behavior if they happen to have the same value. But normally, private variables at some random moment in time would have a spread of values as manifested by variable k. And the rest are mostly solid horizontal lines. So what happens? Here we're using implicit labeling. And what OpenMP implicit labeling does, all the variables which were already declared before the the parallel region will be labeled shared. And as you can see, most of variables actually labeled shared. They all have solid horizontal lines. They have the same values. And certain variables like k, and k here is the index variable for work sharing construct 4. And implicit labeling rule for OpenMP states that those index variables are labeled private implicitly. And that's why you see them as sort of random dots. They're actually labeled as private. This is the correct behavior. You don't want these index variables to be updated independently by different threads because it's going to screw up the this work sharing construct behavior. But the bad situation is with many variables labeled as shared, apparently, because you use it implicit labeling. The bad news is DDT is not smart enough, and I suspect pretty much no other debugger would be smart enough to actually tell you these are the shared variables which are causing this particular race condition bug. But it gives you an indication that these variables can be in danger of creating shared or race condition bug because they are apparently shared. And so what you have to do, you have to think hard. Do they actually have to be shared? That's first order of the business. And even if they have to be shared, you want to make sure different threads do not update them at some random moment of time indiscreetly. You have to serialize that operation using critical section or maybe atomic pragma, something like that. So you have to do something special. But in this case, the example is simple. All you have to do is to make sure that you're not using the implicit labeling. So if you go back, so the fix here is to not to do a beginner's mistake. So don't use implicit label. Instead, use explicit. So you have to say default none. This will force you to think that only some variable has to be shared, as I mentioned before, because it's an argument to reduction clause, and the rules state variable has to be shared to be used as such. And all the rest, all these index variables, both exterior loops, also interior loops, all these scratch variables, x, y max, y, etc., they have no business being shared because this creates havoc. Instead, each thread has to use its own private version of that. And if you use default none, as I really advise everyone to do from now on, then compiler will force you to think which variables have to be shared. The rest has to be labeled as private. So let's save this file and let's compile. And if you execute it, we get correct behavior even with GNU compiler. Every time we run the code, the results are predictable. They're the same, and they're actually correct results. So we fix the bug by dealing with race condition situation. All right, so we have a little bit of time to consider deadlock bug. In fact, I have a few examples of that, and I have time to go one or two of them. So let's consider example 1. So it's very short, very simple example, just a small parallel region. And I'm doing situation which I already described when I was showing the slides. One way to create deadlock is if you use if clause and the argument is thread ID. So here's the ID is thread ID. And I'm saying if my thread ID is equal 1, I'm doing some serialized operation, in this case printing a statement, some serial work. Otherwise, all the rest of the threads, I want to participate in OMP4 work sharing construct, which looks okay, especially if you're a beginner. So let's try to compile this code. X1. So something is going on. So the serial statement was printed correctly, but it ends indefinitely. If you try again, you can wait indefinitely, nothing happens. It doesn't finish. We have signs of deadlock. And so let's try to see if DDT can be of any help. Unfortunately, unlike MPI deadlocks, I'm afraid to say OpenMP deadlocks are much less obvious, the manifestations, when you use a debugger like DDT. That's very unfortunate. But so at the very least, what you're gonna get from DDT. So let me run the code. So this is deadlock, and it's conveniently to deal with by just using it as an MP3 player. So pressing play button. Then you can switch to input-output tab to see that output of your code. So it printed that statement and nothing going on. We can press pause. Unlike MPI, in deadlock situation, in this case, it would actually show me nicely exactly where my code got stuck. And then, in fact, you can go to Tools and then go Message Queues, which grayed out for OpenMP. But for MPI, it would bring up open up a new window where you will see all the communications which are hanging, which have been executed but never been received. So you will see deadlock in action. Unfortunately, OpenMP is much more implicit part of the environment, so debugger doesn't have that information. All you get is there is a deadlock. You can press play again, pause again. It can tell which parallel region deadlock is in, because normally code has multiple parallel regions. So at the very least, you will see which parallel region is affected. It will not tell you which particular pragmas generated or created this deadlock, unfortunately. There are some implicit signs of what's exactly happening. If you go to Stacks tab, normally it should tell you where each thread is hanging currently or stopped at. In this case, you can see all threads are waiting some sort of library level routine, GOMP task wait. So I suspect, I haven't done enough of testing, I suspect this is what you get when you break the main rule of OpenMP, one of the main rules of OpenMP. That is, you have to make sure that all threads reach certain pragmas like OMP4 or OMP single. These pragmas, these work sharing constructs are designed such that all threads have to reach them. If even one thread cannot reach them, you create deadlock. And I suspect this kind of situation is manifested inside DDT as such. So you'll see most of threads get stuck in this GOMP task wait state. So again, I'm afraid it's not as explicit as deadlock detection of MPI codes, but you do get some extra hints by using DDT. So now you get this hint that something is going on. You broke some of the important rules of OpenMP, and then you analyze and remember the prevention strategy. Make sure you don't use thread IDs as argument to if or any conditional clause. And if you do, make sure pragmas like OMP4, OMP single, a few others are not been able to reach by one of the threads, which is the case here. So the solution here to solve this deadlock bug, instead of using if statement, you have to enclose the serialized portion of your code inside perhaps single pragma, which is a work shared construct, or maybe master pragma. And then you, without any if condition, you list the pragma OMP4. In that case, one thread will compute the serialized version, and then all threads included in that thread used for serialized version portion of the code will participate in OMP4. In that case, you fulfill the conditions for OMP4. All threads will be able to reach it, so you will eliminate race condition bug. So let's consider example 3. So what's going on here? This is a different kind of bugs, deadlock bug. That's why I want to show it this work to you. So in this case, you have a parallel sections, 3 sections. So the idea is there are 3 threads, each of them executing one of the 3 sections. And then we have a shared variable flag, which is used to communicate between different threads. So the idea is that we want this section number 1 executed by thread number 1 to do something, let's say print section 1, and then at the end it updates the flag, which is a shared variable, to value 1. Original value is 0. And that would be assigned for the second thread, which is executing second section, to start executing its own, its own section. In this case, just to print section 2 and then update flag again. So the idea is, even though these are 3 parallel threads, but we want essentially serialized execution, we want always these statements to be printed in a certain way. Section 1, section 2, section 3. So, and we're using while, so infinite loop while, which keeps spinning until the shared variable flag was assigned to a specific value. Once it happens, then the section does its job. So let's see if it actually works. Let's X3. So what we want to see to 3 statements, 1, 2, 3, executed in certain order every time we run it. So let's do that. Good. So we have section 1, section 2, section 3. We do it again and again and again. We can try to, with using Intel compiler, the same thing happens again. Great. So we debugged our code using -G capital O0. Seems to be working fine, so we can now submit a job. Okay, we go compiling capital O2. Now we have optimized code. Okay, let's just final test before we submit a job to the scheduler. Oops. We actually have a bug, and a nasty kind of bug, which only manifests itself when you have optimized code. And that's nasty because typically you debug your code, you make sure it works fine using capital O0, because this is just a better way to debug. So in fact, it does manifest itself with levels as low as 1. So, okay, so we have a different kind of bugs. It only manifests itself when you use certain optimization level. If you want to debug this code, we have to use the optimized version, -G capital O1. So let's try to see if DDT can be of any help. So this is a manifestation of deadlock. So let's see if DDT can suggest any hints or cues. So we'll be using 24 threads. We press run. And this is deadlock, so convenient way to deal with it, just press play. Then wait, then press pause. We go to input-output tab, so we have only section 1. So fortunately, unlike the previous deadlock situation, this is more specific deadlock, and apparently DDT has a little bit more information to work with, and it actually tells you something. So some threads got stuck on this flag equal 1, and you press pause. In fact, it has to be just one thread because it's inside specific section. And another hint is, so flag is a shared variable. Remember how you identify shared variables? You have a look at the spread of values. It should be horizontal line for shared variables. In fact, what we see here, we have a spread of values. So certain threads have different value, have 0 value, and the rest of the threads have 1 value. And we can switch through different threads, and indeed you can see value keeps changing. Here it's 1, 1, and we switch into the very first thread, value is 0. So something is really fishy here because shared variables have to have consistent picture, consistent value across all the threads. This is not happening. So we have, on one hand, you know it's a deadlock, and then you know something is fishy going on with shared variables flag because it's inconsistent state. And this should be sufficient to tell you that you are not using this shared variable properly. Remember, to properly communicate between different threads, you have to use flash pragma. After updating shared variable, so after writing, you have to use flash pragma. And before reading by other threads, you have to use flash pragma. So the solution here is to go back to the code. And in fact, I have a solution already. It's example 3a. So what I did, I added flash pragma, specific flash flag. So please be specific. You can just say flash, but it will flash all these shared variables, which can be very, very inefficient. There is no need to do that because we know we need to protect, to do a good job with specific shared variable flag. So that's what we do. We say flash flag. And we do it after writing. So after doing flag equal 1, we say pragma OMP flash flag. Same, this is second section here. And same with the third section here. And also read on the read side. So inside each of those while loops, I'm inserting pragma OMP flash. So those threads which wait for the flag to change its value, they constantly flash check value, flash check value, constantly in a loop. So let's see if that solved our issue. So you see it's optimized code, which was buggy before. So we added flash pragmas. Okay, so bug is gone. So we got the correct behavior. So I'm afraid I have to stop at this point. So the hope is that what I showed you, that DDT is useful for debugging OpenMP programs, though might be slightly less convenient and less obvious as it was with MPI codes, but still can save a great deal of efforts. And please go ahead and use it for all your debugging purposes. It's a great tool, and we purchase it for a reason, so you can use it and improve your debugging experience. Okay, thank you very much for your attention.